start calculating, the thing we want to do is we want to find theta hat, which, given by this theorem over here, should be expressed by 1 minus a weight multiplied by mu plus that weight multiplied by the average of policy observations. I have only one policy I'm looking at, and that policy only has one claim number. So on this given policy, the average of the observations is just that claim number, x. Now you can kind of see that the w depends on some lambda and some phi, and you have a mu as well, and they depend on different things. So the thing that we're going to do first is calculate each of these different expressions, or coefficients, or what we call them. So let me just go here and write mu of, well, mu. So let's start here. We are given that mu is equal to the mean of mu of theta, and we established that mu of theta was the expected value of x given theta. And in our particular case, the mean of x given theta is theta, right? Because x given theta is Poisson distributed. So this is just the mean value of theta. And I don't think we can do more about that, so let's just let that stay. Or can we? Wait. The mean of theta is equal to m1. So we can just write m1 here. So that was mu. And let us also just write lambda here. Lambda is equal to the variance of mu of theta. And again, mu of theta was just theta. So we're looking for the variance of theta, which is the second moment minus the first moment squared, right? So we also have an expression for the variance of theta. The next thing we want to find is the phi, which is given by the mean of v of theta, where we recall that v of theta is the variance of x given theta. And since x given theta is Poisson distributed, we once again have that variance is just theta, and this is just equal to m1. So to cap it all off, let's just write this stuff inside our formula. What we have as well is that, let's just write w here as well. W is equal to ni, and ni is the number of observations for the ith policy. We only have one claim number, so ni is just 1. So it is 1 multiplied by lambda divided by phi plus 1 multiplied by lambda. And now we can write up the expression here, which is 1 minus, should probably change a color. It is equal to 1 minus m2 minus m1 squared divided by m1 plus m2 minus m1 squared multiplied by m1. And then plus, we have w multiplied by x, where w is equal to m2 minus m1 squared divided by m1 plus m2 minus m1 squared multiplied by x. Now it's kind of tiresome to have to write this up twice each time we work with, say, theta squared in the future, so the thing we'll do here is just rewrite it into m1 plus, and then we have x minus m1 multiplied by this fraction here, since it appears 2 times. I really don't like this color that I've chosen for these calculations. It's this weird bubblegum color, so I apologize for that. Okay, so now we have theta squared. Let's also write up the linear Bayes risk theta rho of theta hat. which is given by this formula here. It's 1 minus w multiplied by lambda. So let me just write the calculations for that. Rho of theta hat is equal to 1 minus w, then multiplied by lambda, and lambda was equal to this thing, so m2 minus m1 minus m1 squared. And I mean, we can also just multiply this in there if we want to. Doesn't really make that big of a difference, but I guess it's nice to get rid of the 1. So I have m2 minus m1 squared, this thing squared, since I'm multiplying this into the numerator, divided by m1 plus m2 minus m1 squared. And I think that the two expressions that we have now, this one for the Bayes linear Bayes estimator and this one for the linear Bayes risk, they are also the two expressions that you find in the PDF solution of A, which is nice. I mean, we have now established that this is it, and we will not use this in B, so we're done. However, the PDF solutions are done in another way, and I think I will also try to solve it according to those solutions so that you can see which formulas we use and get acquainted with the more general notation as well. So that is what we will talk about in the next video. See you guys there.